Welcome back. So let's try to apply these steps. Fine. And we already have the FSM. This was a finite state machine of a sequential circuit that had one off state and three on states. And the first transition, that is a transition from off state to on one state, it was governed by the external input B. If B was high, then only I can move to off to on one. If B continues to remain low, I will continue to stay in this off state. Fine. Thereafter, once you have reached on one, from on one to on two, from on two to on three, then from on three to off state, you don't need to actually look at the value of the input B. It will automatically, it should, I mean, since we have to design it, it should automatically happen with the rising edge of the clock. Fine. So the only transition that is governed by the external input is a transition from off to on. So this is a typical FSM. It has all the characteristics of the finite state machine. There are a finite number of states. So maybe I should summarize here that in this number of states is equivalent to 4. Right? Then there is an initial state as defined by this arrow. Every state has an output given, and we have complete information if I am in a current state, how I can move to the next state. So the first step, which is capturing the finite state machine, it is there. Now the second step is we have to create the standard architecture. Fine. And in that standard architecture, we have to specify what is the width of the state register. Fine. So the standard architecture is the same conventional architecture. It will have a combinational part. Let me just copy the same thing. And this part. Fine. Then there will be external input. In this case, my external input is input B. I will get an output which is X. So these things are pretty straightforward. B, X. This is the combinational logic. And this is my clock. It's implied. And this is my state register. Now the question is, what is the width of the state register? And that directly depends upon the number of states you have. Now in this case, we have 4 states. 4 states means 2 raised power 2 since we are dealing with binary. So this means to explicitly represent these 4 states using binary codes, you will need 2 bits. Right? Like off, you can say 00 to represent off. On 1, you can say 01. On 2, 10. On 3, 11. Fine. So this means you will need a 2-bit state register. Fine. And that will define our output, something like this. Sorry. Then to complete this, so this is what I mean by standard architecture. Fine. So let's call this S1, S0. These act as inputs. And let this be N0 and this one be N1. Fine. So I have B as an external input. X, it is the output from the current output from the sequential circuit, or you can say the finite state machine. Then in this case, S1 and S0 represent the state inputs. That is the output of the state register that act as input to the combinational logic. And N0 and N1 represent the next states. Fine. So this is what we create the standard architecture. Then the third step is we have to encode the states. Like I said, we can't implement it like it. So encoding, you can assign a code. So I will redraw my finite state machine. And this time round, I will not use these character names of on one, on two, on three. I will actually code them. So let's assign 00 to this state. On 1, that's represented by 01. On 2 by 10. And on 3 by 1, 1. The rest remains the same. So you will have an initial state. Every state will have a defined output. And then there will also be transitions from one state to the next. So this is the third step wherein I have encoded my finite state machine. Fine. Then the fourth step is creating the state table. Fine. So the way we create the state table is similar the way we do it for truth table. So what we do, we list inputs on one side and outputs on one side. Fine. Inputs on one side, outputs on other side. Fine. And we have different categories of inputs and outputs. For example, when inputs are concerned, I have the external input B and I have the input that comes from the state register. So in total, I have three inputs, S1 and S0. These are from the state register. B is my external input. Similarly, when outputs are concerned, I have three outputs. One direct output X and N1 and N0 that represent the next state. So we have state input, state outputs, external input, external output. Fine. Now let's create the state table. Now if I start, my initial state, as you can see, is a state 0, 0 off, which I have encoded as 0, 0. So if I have, maybe I should actually draw it like a table so that we can follow it properly. So six, then like this and this. Similarly on this side. Let's start filling it up. So my current state is 0, 0. Right? And in this state, regardless of what the input B is, my output is always 0. Because once you are within this state, output is 0. Right? Now I have to determine from this state what is the next state that I can go to. Now that actually depends upon the value of 0. So if the value of B is 0, I will continue to stay in the same state, which is 0, 0. Then another combination can be I am currently in this state, which means my output is 0. But if the value of the external input is 1, then I can move to the next state, 0, 1. Then I am in the current state 0, 1. Thereafter, the value of B doesn't matter. This is important because the B was governing the transition from 0, 0 to 0, 1 that we have captured in the state table. So this means when I am in this state 0, 1, first my output will be 1, and then regardless what the value of B is, I am always going to go to 1, 0. So if B is 0, doesn't matter. If B is 1, I will still have the same output. I will still have the same next state. Similarly, when I am in 1, 0 state, if B is 0, B is 1, doesn't matter. My output will be 1, and I'm always going to the next state 1, 1. Then when I am in the state 1, 1, B is 0, B is 1, doesn't matter. I'm always having an output of 1, and I'm always going to the state 0, 0. So this actually creates my state table. Fine. And then you have to solve this. The fifth step is we have to implement the combinational logic. So we will come up with the equation for x, we'll come up with an equation for n1, we'll come up with an equation for n0, then we'll implement it just like we did in combinational circuits. Fine. So the best way of solving this is, again, we will use our k-maps. So let's have a k-map here and we'll solve it one by one. I'll try to fit in this space. I need three of them, so maybe I can copy paste them. I have three input variables, so I will be using this kind of a k-map. And I will have S1 complement, S0 complement, S1 complement, S0, S1, S0, S1, S0 complement, and along this side B complement and B. So just to save some time, let's copy it. Fine. So the first one we'll be using for to solve x. So this one will be using to solve for x. So apart from the first two cells, again you can visualize it in terms of min terms. Apart from m0 and m1, it's high everywhere. So if I fill it, it will be 1, 1, 1, 1, 1. Then you can combine it using the laws of Karnaugh map. You can have different combinations. You can have a chord like this, then another chord like this. Fine. This will give you a simplified expression for x. I think it will be, for the green one, it will be S1. For the blue one, it will be S0. So x is S1 or S0. Fine. Similarly, we can solve for the outputs N1 and N0 by using these coordinate maps. For example, let's solve for N1. So it is M0, M1, M2, M3, M4, M5. M0, M1 are not there. M2, M3, M4, M5. Fine. Again, you can have some combinations. Can combine. We can't have a chord, but we can have two adjacency. Fine. So this will give me my N1 as S1 complement S0 plus S1 S0 complement. Yeah, you can say this is an XOR operation. And I can say this. Fine. Then finally for N2. N2 I have M1, 4, 5. So M1 will be here. 2, 3, 4, 5. This maybe you can come up with combinations like one could be this. Then I can fold it and have another adjacency like this. This will give me an equation for N2. Sorry, N0 it is. It is N0. Fine, so we'll have S1, S0 complement. Then for the red one, we will have S0 complement dot B. Fine. And then you can use this. So we have to now create an architecture. I don't need this. Yeah, let me try to fit in here. So what we already have is the state register. We have already specified the contents of the state register, that it is going to be a 2-bit state register. So this we have done, 2-bit state register. It will have a clock that is here, which means I will be having two inputs from this side, S1 and this one is S0. Fine. Then I already have the input B. Let's use a different color for that. I have the input B. Say this is B. Fine. So this one is S1, this one is S0, and the blue one is my external input B. Okay, so using this we can implement it. So X, we need an OR operation. With inputs from S1, S0. Then for N1, I need an XOR operation. And this N1 will go here and will be stored in the 2-bit state register. Fine. Like this and this. Then for, okay, this is slightly complicated. N0, I need S1, S1, then dot S naught complement, then S naught complement, and an input from B. Then combining these two using an OR gate will define N0, and that will be fed back to this state register. So this is the overall sequential circuit that will implement the behavior which we specified using this finite state machine. Right? So these are the steps we have to go through. Right? As you can see, the most important step is you should be able to correctly capture your finite state machine. Once you do that, then the rest of the steps will follow. You will create the standard architecture wherein you will specify the width of your state register. That will actually depend upon the number of states. Like in this example, we had 4 states. We express it as a power of 2. So this means we'll have a 2-bit state register. Fine. Then we'll encode the states using a unique code for each state. Then we create the state table wherein on one side we list the inputs and on the other side we list the outputs. Inputs you will have two types: external input, which may or may not be there, and state inputs, which will always be there. Similarly, on the output side, you will have an external output. Again, it may or may not be there depending upon the problem and the next state. Now, in this case, we had all the inputs, we had all the outputs. You'll gradually see, you'll take some examples wherein some of them will be missing. Then from the state table, just like we entered the truth table, and for every entry we specified what the output is, we follow the same process, then simplify it using the Carnot map technique, get the simplified equations, then implement them. And I mean, this basically is whatever I have drawn here. This is basically the combinational. In the standard architecture, it is this part which we resolved. Fine. This was already resolved, and we resolved this one. And by resolving this, you will get your sequential circuit implemented. Fine. We'll take some practical examples, some designs that are a part of your curriculum, and we will design them using the FSM approach rather than design them directly. We use the same approach in the combinational circuits. I told you that in this course, we will follow the designer's approach rather than the simply analyzing. Right? So we'll come up with the design problems, capture their finite state machines, and ultimately following this methodology, try to implement them. Stop.